Hi, I'm Aaron Casserly, and I'll be presenting about my work with the Portland State Aerospace Society, um, uh, in particular MDO, or Multidisciplinary Design Optimization, for their Launch Vehicle 4, which is the fourth iteration of their rocket. And so MDO is a field in which you can solve complex engineering problems involving multiple technical specializations, and also involving multiple design and performance constraints. And this is not the physical side of engineering where you're manifesting something. This is the software and mathematical and physicsy side of engineering where you're finding an optimal design using a computer. And so the research statement was mainly to improve and extend the MDO simulation code that existed on the PSAS's GitHub. And so I went ahead and did that and fixed some issues and added some new features to help optimize the design of the rocket, and overall to minimize weight and system complexity without sacrificing the vehicle apogee, because it wanted to be above 100 kilometers. And so what I set out to do was to refine the aerodynamics model, update the design that is fed into the optimizer, just by communicating with the team as to modifications that need to be made to the digital file that represents the template rocket that is fed into the optimization software. Do a bit of simulation of fin staging, which is basically to if I have an initial larger fin can with larger fins at liftoff, then this increases the vehicle stability and would reduce the required power of the engine at takeoff, and then also dropping that larger fin can would effectively reduce drag in upper atmosphere because you have smaller fins. And so I wanted to try and simulate that. And then structural analysis outputs throughout flight. Also comparing the merit function evaluation of the different optimization approaches to see which is best. And so a merit function is basically constructing an evaluation of a design based on combining the performance of the rocket, because we simulate the trajectory of the design, and also adding a penalty component, which is its performance in relation to the constraints that we desire to meet. And so results were that I created or modified the aerodynamics model and improved the fin body interference aspect of the aerodynamics model. The noticeable change in the design vector was that the nozzle exit pressure increased, which indicates that the fin body interference is more accurate. And so basically a larger exit pressure was optimal given the more accurate fin body interference, which indicates that what nozzle exit pressure is doing is basically dealing with nozzle overexpansion versus underexpansion. And so this is basically where you don't want you don't want to see like the propulsion or the effectively the fire fanning out when it leaves the nozzle, or being much smaller than the nozzle. You need an exit pressure such that you're getting the optimal amount of thrust. And so there was that. And I also ended up converging on the ideal design. And so I did that first by achieving feasible fins and a 95 kilometer apogee with a 9 kilonewton engine. And so while this was good, the stability was still minimum stability of the rocket was still a bit higher than the minimum that we desired, and so or the minimum acceptable. And so I scaled down the fins, and this improved it. This was even better, and reducing the fin area actually led to an apogee of 107 kilometers with a 9.8 kilonewton engine. And so the Aerospace Society it should be going ahead and manifesting the rocket according to those specifications. And so the slight problem was that there was a little bit of a vehicle drift. This is probably somewhere in the software. There was an error leading to a sort of translational motion that wasn't exactly described by the wind or the Coriolis acceleration or Coriolis effect. And so a bit further debugging there would be required. But overall, this was my work, and thanks to Andrew Greenberg, Peter McLeod, Max Eldsroth, Corey Gillette from PSAS for providing guidance, and Professor Benjamin McMorran from the U of Physics Department. Thank you so much for listening.